So this is the last lesson in this pre-calculus unit, and like most of the lessons in this unit, this is meant to be somewhat review, although this probably has the most new kind of direct concepts, or I should say direct examples, new direct examples compared to the previous lessons, and still working with inverses. And so first this lesson is focusing on three specific inverses, and these are the inverse trigonometric functions. Now you've been dealing with inverse trigonometric functions since you first learned about trigonometry. Most likely you've been using buttons on your calculator for inverse sine, inverse cos, and inverse tan. And keep in mind, every time you use one of those buttons, chances are you don't really understand what it's doing. You're just going through a process. But in general, you use the inverse sine function when you're trying to find an angle, which is the reverse of the sine function. To use a sine function, you have to know the angle, and it tells you the ratio. The inverse sine is the other way around. You put in the ratio, quite often as a decimal, and it tells you the angle. So I really want to focus on these functions and some characteristics of them. So first of all, the inverse sine of x, which we can also say arc sine, and the inverse cos of x, which we can say arc cos, inverse tan, we can say arc tan. And generally, I'd rather say arc sine than inverse sine, just because it's a few less syllables, but it means the exact same thing. But the inverse of sine, and I don't want you to think that arc sine is somehow anything different than what you've been dealing with on your calculator. But the inverse of sine, that arc sine, is the inverse of just part of the sine function. It's not actually the inverse of the entire sine function. And that's because if it was the inverse of the entire sine function, then arc sine would not be a function. You put one number in, you get multiple numbers out. And I'll talk about that in a bit. So the inverse of sine, every time you've used it, it's actually just the inverse of sine with this restriction. So it's the inverse of only this part of sine. It's only the inverse of sine from negative pi over 2 to pi over 2 if we're dealing in radians. Negative 90 degrees to positive 90 if we're dealing in degrees. And arc cos is the inverse of only this part of cosine from 0 to pi, or 0 to 180 if you're thinking in degrees. And arc tan is only the inverse of this one section. And every single time you've used one of these functions, while we call it the inverse of sine, it's really just the inverse of part of the sine function. So first, let me talk more about that. Let's look at sine. Okay, first let's think about what just the graph of sine x looks like. Starts at 0, goes up to 1, goes back down to 0. Oh, helps if I pay attention to the scale of my graph. Goes up to 1, goes back down to 0, goes down to negative 1, and so on. And I'll kind of show it on this side as well. All right, so what I'm going to kind of sketch out is sine of x. And I will say, if I was to deal with if arc sine was the inverse of all of this, I could figure out what it would look like by just swapping around the coordinates. For example, arc sine I know would go through 0, 0. This point right here, and that's at pi over 2 comma 1, would be at 1 comma pi over 2, so right here. And this point right here, which is at negative pi over 2 comma negative 1. The inverse of that would be at negative 1 comma negative pi over 2. And this point right here, which is at 3 pi over 2 comma negative 1, would be at negative 1 comma 3 pi over 2, which is right. Why can't I see down here? There we go. That doesn't seem right. What am I doing wrong here? 3 pi over 2 comma negative 1. Now it's at negative 1 comma 3 pi over 2. Why doesn't? Oh yeah. I forgot about this point. That's why. Sorry. That point is correct. It's a little more obvious if I plot this point right here that I'm highlighting in kind of pink. That's at pi comma 0. So the inverse would be at 0 comma pi. There we go. And notice what I start to see is a wave like this. And so again, what I've sketched out is the inverse of all of sine. And notice what I'm sketching out is not a function, which means if this is what you've been dealing with every time you've been dealing with the inverse of sine, then for every one value you put in, there's multiple values that come out. There's an infinite, actually, values that come out, because this wave, keep in mind, just keeps going on and on forever. And so that's never happened. You've never gone inverse sine on your calculator and got an endless list of possible values. You've only gotten one. And that's because, again, arc sine is the inverse of only part of sine. So now let's pay attention to this restriction here. Negative pi over 2 to pi over 2, that's this part from, make it nice and dark, from here to here. So that is the only region that arc sine is actually the inverse of. And so if you think about how that's going to affect the shape of arc sine, that means arc sine is actually only from here to here. And that is the graph of arc sine. And another way of thinking about it is the domain of sine is restricted to negative pi over 2 to pi over 2, and therefore the range of arc sine is only from negative pi over 2 to pi over 2, and that's what I'm seeing on my graph. And so again, arc sine is the inverse of only this part of sine. And every single time you've dealt with the inverse of sine, without realizing it, you're probably actually only dealing with the inverse of this one part of sine. And so the domain of this restricted variation of sine is from negative pi over 2 to pi over 2. So like I mentioned before, notice the range of arc sine is the exact same. And the range of sine is from negative 1 to 1. And notice that's the domain of arc sine, which again, we've seen from the beginning of learning about inverses that the domains and ranges are swapped around. And so again, every time you deal with arc sine, you're actually just dealing with this function that's kind of drawn in red, but not the dashed part. And so to go through this a little bit faster now for the others, for cosine, I'm just going to go straight to drawing cosine just from 0 to pi. So cosine starts at 1, goes down to 0, goes down to negative 1, and I'm going to stop there because that's my restriction. And so this is what the graph of cosine looks like if we only look from 0 to pi. And so for arc cos, it's going to go from here to here to here. And it's going to look something like this.
Dennis, can you please see Rick in the office? Dennis, please see Rick in the office. Thank you.
And that's arc cos. And again, I could draw the rest of cosine as a dashed curve, and therefore visualize what the, how that would correlate with the rest of arc cos if it continued, but it doesn't, so I'm not going to draw any more than that. All right, and so again, the restricted domain of cosine when dealing with arc cos is from 0 to pi, and so that's the range of arc cos. And again, the range of cosine, even when restricted, is still from negative 1 to 1, and so that's the domain. Okay, and lastly, tan and arctan. Again, tangent. First of all, tangent, let me draw this here, goes through 0, 0, goes through pi over 4 comma 1 and negative pi over 4 comma negative 1. But tangent, if you look at this restriction from negative pi over 2 to positive pi over 2, notice it doesn't include those, and that's because those are asymptotes of tangent. So if I sketch this out, tangent looks something like this. And there's my graph of tangent, restricted from negative pi over 2 to positive pi over 2. It's just that one full cycle. And so therefore, when I deal with arctan, I'm going to have horizontal asymptotes at pi over 2 and negative pi over 2. And that's the graph of arctan. And to be honest, the graphs of arctan, arcsine, and arccos aren't really that important as long as you realize, how they relate back to, tan, cosine, and sine. And so again, the restricted domain of this tangent function is from negative, sorry, it should be a round bracket, because we don't include negative pi over 2, negative pi over 2 to pi over 2, and that's the range of arctan. And the range of this restricted variation of tangent is all real numbers, and notice that's the domain of arctan. All right, so let's work with these a little bit. And again, you've been working with inverse trigonometric functions since grade 10, maybe even earlier, but we haven't been focusing most likely on what these functions are. So I want to find the arc sine of 1/2, okay, which is the same as asking for the inverse sine at 1/2. So what does that equal? Well, let's think about what it means. This means I want to think about sine. Well, that's too big of a marker. I want to think about sine of something equals 1/2. But that something has to be within that restriction from negative pi over 2 to pi over 2. If we don't have that restriction, you may recall there's actually an infinite number of correct answers here. Solving where does sine equal pi over 2, there's countless places where the sine wave equals 1/2. But again, we're only looking from negative pi over 2 to pi over 2. And so where does sine equal 1/2 in that restriction? At only 30 degrees, or only pi over 6. Oh, these darn thick markers I've created. And so therefore this equals pi over 6. Or 30 degrees if you're in degrees. But we'll almost never use degrees in this course. All right, so similarly, the arc cos of negative pi 1 over root 2, we have to think about where does cosine equal negative 1 over root 2. And again, but this time only in this restriction of where cosine is between 0 and pi, or 0 and 180 degrees, which is really the first two quadrants. And so where does cosine equal negative 1 over root 2? Well, because it's a negative, maybe it's a little helpful to visualize my angle in standard position. Cosine is negative in these two quadrants, but if I'm looking at this restriction, 0 to pi, that's the first two quadrants, so I'm going to ignore this possibility right here. And so the angle we're looking at must be this angle from here to here. So what's that angle? Well, I got to think about my reference angle. And for that, I look back at here and realize it's 1 over root 2. Well, cosine of 45 degrees, or the cosine of pi over 4, is 1 over root 2. So pi over 4 must be my reference angle. And therefore, this angle from here to here must be 3 pi over 4. Really, the vast majority of this is remembering some core ideas, some fundamentals of trigonometry from pre-calculus 12. And understanding that, utilizing the castle, remembering that cosine is negative in some quadrants, positive in some quadrants, how it relates back to the reference angle. A lot of little things to come back to. And if I, again, if I didn't have this restriction right here, if I just asked you where does cosine equal negative pi over 2, not only would there be another solution in this quadrant, but there'd be countless solutions actually, because you can go around and around as many times or go backwards as many times as you want. But that restriction makes it so there's only one solution. Hence, these are all functions. Hence, I put one number in this case negative pi 1 over root 2, and I get one number out. Lastly, I have the arctan of 3 pi over 4. Now you may be tempted to look at these and go they are inverses, so they cancel each other out. Yes and no. We got to be careful, and that's because arctan is the inverse of only part of tan. And notice what I'm putting into the tangent function is 3 pi over 4. That's what I'm putting inside the tangent function. But if I look back at arctan, 3 pi over 4 is not even inside that restriction. So we just got to be careful. So that said, how do I deal with this? Well, let's first focus on the inside. Let's think, what is a tangent of 3 pi over 4? Okay, so like before, let me go back to my cast rule here and think about where is 3 pi over 4? 3 pi over 4, I can visualize is right here. And so I know the reference angle is pi over 4. And why does that matter? Because this being 3 pi over 4, I know that the tangent of 3 pi over 4 is going to be the exact same as the tangent of pi over 4, but negative, because in the, if I go like this, in the second quadrant, only sine is positive. So I know the tangent of 3 pi over 4 is negative, and negative what? Negative whatever the tangent of pi over 4 is. And the tangent of pi over 4 is 1, so the tangent of 3 pi over 4 is negative 1. That said, what I've done now is I've figured out what the tangent of 3 pi over 4 is. It's negative 1. That said, all of that is now going inside arctan. All right, so now what's the arctangent of negative 1? Well, that means tangent of something equals negative 1, but only within the restriction of negative pi over 2 to pi over 2. So where does arctan equal negative 1? Well, this angle I've sketched out right here is not inside that restriction. Right? This angle I've sketched out right here does show me where tangent equals negative 1, but it's too big. It's 3 pi over 4. My restriction has to be only up to pi over 2. So, it's either not possible or there has to be another place. And again, tangent is negative in the second quadrant and the fourth quadrant. And so we want to pay attention to what this angle is, which must have the same reference angle, but going backwards. And that is within that restriction. So if I go backwards, then that is within the restriction. And so I now know that this must equal negative pi over 4. And so a good example of a tricky question that requires lots of tiny little steps, doesn't really require anything new once you just remember that arctan is the inverse of tan from just one interval, but lots of details going back to the beginnings of trigonometry in pre-calculus 12. When I say beginnings, I don't mean to say that somehow should be easy, but it should definitely be familiar. All right. With that said, the last two examples are looking at what happens when I put sine and arcsine into one another in different ways. So for this example, I have sine of arcsine, and the last example is arcsine of sine. Okay. And for this, again, you may look at this again and be tempted to say they cancel each other out. But again, yes and no. It all goes back to the fact that the sine function, is a function that has a domain of all real numbers that goes on forever. But arcsine is only the inverse of part of sine, not the whole thing. And so if we're not sure what this looks like, which I don't blame you, let's make a table of values. And notice my scale. I got whole numbers on both my scales. I don't have any variations of pi, and there's a reason for that. That said, pick a number for x and figure out what happens for y. And I would always start with 0 instead of 1. And when x is 0, let's see what we get for y. I have what x is 0 right here. First, I have to think about what the arcsine of 0 is. All right, which means sine of what equals 0? Okay, well, the sine of 0 equals 0. Okay, so all of this is 0. And now I have the sine of 0, which is also 0. So I'll just kind of write, there we go. So when x is 0, y is 0. A lot of little steps I have to kind of talk about, so it got a little messy here. But essentially, every time I'm putting the value into arcsine and then sine. So 0, 0, let me plot that. Nice point to plot. Okay, let's pick another number. You may be, why not just pick 1? And if it isn't pleasant, pick a different number. But let's pick 1. I think 1's a pretty pleasant number, which means I put 1 right here. And I have to think about what's the arcsine of 1, which means I have to think about the sine of what equals 1. Well, the sine of pi over 2 equals 1. So the arcsine of 1 equals pi over 2. And then I put that into sine. So I have to think about what's the sine of pi over 2. And the sine of pi over 2 is 1. So notice I put in a 0, I got out a 0. I put in a 1, I got out a 1. So let's not jump to a conclusion too quickly, but that's fairly pleasant. So you may assume if I put in a 2, I'm going to get out a 2. Well, let's see. Let's put a 2 into arcsine. And every time my process is the same. The arcsine of 2 is going to equal whatever, I think about the sine of what equals 2. Well, that's not possible. Sine never equals 2. So the biggest value sine by itself can get to is 1. So the sine of 2 is not possible. So now I know for sure it's not as simple as whatever number I put in, I get out. Let's put it in, how about negative 1? If I put in negative 1, then I want to start by finding this arcsine of negative 1, which means I have to think about where does sine equal negative 1, which is possible. That's at negative pi over 2. And then I put negative pi over 2 into sine, and the sine of negative pi over 2 is negative 1. Okay, at least I can do that. So that's a nice easy point to plot. So right here. And at this point, if I put in negative 2, I'm going to have the same problem as before with when I put in a 2, because then I have to think about what's the arc sine of negative 2, which means the sine of what equals negative 2. But again, that's not possible. The biggest value that comes out of sine is 1. The smallest value that comes out of sine is negative 1. And so again, that's not possible. And so I can actually see what my graph looks like. It must go from negative 1 to 1, and that's it. As soon as x is bigger than 1, it's not possible. As soon as x is less than 1, it's not possible. Which we can also kind of notice, and you may have noticed this right away. If I just go, before I even go to my table, if I just look at the equation, I have a composition of functions here. And if I look at just arc sine, the domain of arc sine is what? Let's go back here to remind ourselves. The domain of arc sine is the same as the range of sine. The domain of arc sine is only from negative 1 to 1. So it shouldn't be a surprise, since that's my inside function, that as soon as I try to put in values that are less than negative 1 or more than 1 into arc sine, my function kind of can't be evaluated. And so I'll just kind of make a note here. The domain of arc sine is negative 1 to 1. And that makes sense then that since that's my inside function, that my graph also has a domain from negative 1 to 1. So lastly, what if I do it the other way around? What if I have arc sine of sine? And so notice right now, the sine of x has a domain of all real numbers. So automatically I can tell this is going to be different. So that's it. Let's do the same thing I did before. Let's make a little table of values for x and y. And I'm going to start with 0 for the x and figure out what comes out for y. So the sine of 0 is 0. And so then I take 0 and put that into arc sine. And the arc sine of 0, what does that equal? We'll have to think about, where does sine equal 0? Well, at 0. Okay, so 0, 0. Let's plot that. Notice my scale is different here. My x and y's are both going up in variations of pi. And again, there's a reason for that. And that's because the first value I'm putting it into the sine function, and it's easier for me to put in values that are multiples of pi if I'm putting it to the sine function. So next, why don't I put in pi over 2? Why pi over 2? Because I know the sine of pi over 2 is exactly 1. And so if the sine of pi over 2 is exactly 1, that means this part right here is going to be 1. And then I have to think about what's the arc sine of 1. And the arc sine of 1 means the sine of what equals 1. Where does sine equal 1? At pi over 2. So, seems like, again, everything I put in is the same thing I get out. But we saw that last time, that doesn't necessarily continue. But let me plot that. Pi over 2 on x, pi over 2 for y. All right, so let's put in pi. Let's see if I get pi out. Well, if I put in pi, I have to think, what's the sine of pi? The sine of pi is 0. Okay, then I put 0 into arc sine. And I think, what's the arc sine of 0? That means, where does sine equal 0? Well, sine equals 0 at 0. Because that restricted, because of how arc sine is the inverse of just part of sine. So notice now suddenly things change. I put in a pi, I get it a 0. It's a lovely number, 0, but I'm not getting the same thing. So I put in pi, I get out a 0. Okay, well, what would happen next? So now things have changed. Suddenly it's going back down. Let me just kind of show you a couple more quick values and then kind of realize what the graph must look like. Because at this point, we can just keep plotting more points and start to get a sense. So for example, if I put in 3 pi over 2 for x, so the first thing I want to do is find the sine of 3 pi over 2. The sine of 3 pi over 2 is negative 1. Then I have to find the arc sine of negative 1. The arc sine of negative 1 is going to be negative pi over 2. And if I put in 2 pi, first I find the sine of 2 pi, which is 0. But then I find the arc sine of 0. And the arc sine of 0 is 0 again. And I can just, I'm doing these quicker now because I've talked about these same sort of things a lot. And so if I plot these points, I'll start to see that it goes down to here, and then goes back up. And it looks like I have a wave. But I guarantee if you plot the points in between, you won't get a curve. You'll get these straight line segments. And I can continue it this way. But what you get is a pretty weird graph. It's this sort of sawtooth pattern. And the reason we're getting these weird graphs when we're putting inverses inside each other is because arcsine is not the inverse of sine. Arcsine is the inverse of only part of sine. And hence, they don't completely cancel each other out like you would expect with inverses. And I guarantee if you graph these in Desmos, you'll see the same thing. Okay, that's it. The most important part of these questions is not memorizing these graphs, is really just getting familiar with arcsine and sine, and same thing for cosine and tangent. And understanding where I'm getting these values from. If anything seems random here, then really it goes back to these sort of questions right here. Which, with that said, not only completes this lesson, completes this first unit in terms of lessons.